Welcome NPTEL, a basic course on electric and magnetic circuits. We are in module 4 dealing with 3 phase circuits, and in this module we will be dealing with balance current and voltages, also the unbalanced form, star and delta connected loads and generator also. Then we will talk about 3 phase reactive power and active power, and also we will be dealing with 3 phase power measurements using wattmeter. In overall, such a 3 phase circuits happens to be there for handling large scale power system, both rotating as well as the transmission, generation and load also. So, in the first lecture we will be exposing to basics on 3 phase systems, where we will be addressing the balance and unbalanced loads and voltages. Now, let us recall back in our second module on AC system, where we are exposed to voltage, current, sinusoidal in nature as shown here. So, this is a voltage signal for a 50 hertz system. So, 1 by 50 gives you 0.02 second. This is 1 cycle, corresponds to 2 pi in omega t terms, theta term, and this is pi. So, such a sinusoidal signal V t can be represented in terms of phasors, like 5 point with a 0 degree, 5.5 volt with 0 degree, 7 with 20 degree ampere, and so and so. Now, in a system like that, we have a source, we have a load, and the source and load are being connected through a line, cable and so. So, we require essentially 2 conductors to connect the source to the load. Now, in this case, the corresponding current phasor can be expressed in terms of V by Z, where Z is a complex number and V, the phasor, is also expressed in terms of the complex number, polar form or rectangular form, and the corresponding current happens to be also complex form, the phasor current. The real power P is expressed in terms of V I cos phi, where cos phi is the power factor, active power upon the apparent power, phi the angle between voltage and current. The reactive power Q happens to be V I sin phi with unit of var, and the complex power S equals to P plus J Q, with that becomes equals to I square Z or V square by Z conjugate and so. So, we see here that such a load, such a system is called a single phase circuit, where this load can be an LED bulb, a fan and so, and then that is connected from our supply system, let us say 230 volt 50 hertz supply in our house, and connected through switch or so to our load, individual load. So, the corresponding voltage is expressed in a sinusoidal quantity. So, also the corresponding current can be expressed in terms of a sinusoidal quantity. Now, as I said, our house is provided with a L for line or the called also phase, and N for the neutral wire, and then we have fuse, meter and so, and connected to different bulbs, fan, etc. As already earlier also mentioned, we have phase wire, we have neutral wire, and we have an earth wire. For the earth wire is for the safety purposes. So, this supply system is used for the typically we call it a single phase system, and if the corresponding our house load happens to be 1 kilowatt, 2 kilowatt load, then the supply agency provides us a single phase supply system as mentioned here. but when the corresponding load increases 5 kilowatt or so, the agency provides us a 3 phase supply system. So, we will try to understand what the 3 phase system is. 3 phase system is widely used in power high voltage system like a transmission system. We must have seen transmission towers having conductors, several conductors connected there, 3, 6 phase conductors, then the earth conductor in the top and so. Now, you must have also seen big induction motor or drive systems having in industry or so, or even big pump house and so, even sawmill and different machinery also. So, the 3 phase induction motor or different motors also drive system are also 3 phase in nature, like as compared to a single phase induction motor or fan is having small power like 60 watt, 100 watt and so. At generating stations, we have 3 phase generators. Small generators we also see connected to a residential building like a hospital for emergency power supply and so. But at large generating stations, thermal plant, hydro plant, we have hundreds of megawatt of big generators, 3 phase generators. They produce power of 3 phase power voltage. Solar plant, wind farms. Now, these are in solar plant we have solar PV solar gives us DC and the DC is converted to AC through inverters, and from that inverters we get the 3 phase voltage which are being step up through transformer to very large scale for the large scale power station to 400 kV, 765 kV and so. Now, these 3 phase systems have their own advantages, like we will learn through during the study also that 3 phase transmission has obvious advantage that you do not require the neutral conductor, there is economically it is more better in terms of conductor requirement and so also. In rotating machines also like generators and motors, we have advantage in terms of material investment, in terms of efficiency, space requirement and so. Also they have other advantages in terms of technical perspective, rotating magnetic field and etcetera, in terms of power quality also. So, there are obvious advantages of 3 phase system as compared to the single phase, and that is why it is widely applicable, widely used in power system applications and so. So, with our progress on 3 phase systems, we will learn and appreciate. Now, on basics on 3 phase power generation. So, we mentioned earlier a sinusoidal signal is expressed like this, but when it comes to 3 phase system, if you see the waveform here. So, red is corresponds to the Boyer voltage, R phase voltage, Y corresponds to the Y phase voltage and the blue one corresponds to the B phase voltage. So, if you see here this corresponding waveform, then we see R Y B and repeating R Y B and so and so. So, this corresponds to the 3 phase system waveform. So, let us go by that. So, we know that a conductor when it is moving under the influence of north pole, suppose it gives a direction of voltage in one perspective, then when it is under the influence of south pole, then the corresponding polarity of the voltage reverses. Similarly, if you take a coil, then the corresponding under the influence of north pole, the corresponding voltage polarity direction will be reversed when it goes to the north pole and so. So, we say that in a 3 phase alternator we have a distributed winding and we have different phases. Typically mentioned at red phase, yellow phase and the blue phase as mentioned here. So, this is about the 3 phases, the R phase, Y phase and B phase 3 phases. So, let us consider this individual one phase here, another phase here and a third phase here. So, they do produce the voltage simultaneously as mentioned here. If this is your time axis or the omega t axis, then the corresponding voltage waveform becomes like this. So, so the point here is that these three windings, three phases can be connected in different ways. One is the star connection way, which we have already seen in case of DC as well as AC connection also. We know how the star connection is being achieved. So, this R phase and the R to R 1 and R and this is Y 1 Y and this is B 1 B are the terminals of the different three phases, individual phase. So, you connect the R Y 1 R 1 Y 1 and B 1 and that becomes your star point, we call it star point, and then we take the terminals from R Y and B and this gives you the corresponding three phases connection, three terminals for the three phase connection. So, if you see this connection here, it looks like this: B 1 Y 1 R 1 connected here to the same point, star point, and then we have the corresponding R Y and B are the corresponding three terminals of the three phases. So, this is about the source or the generations or the supply side, and we can connect through wires or conductors or cables to the load side. So, the load can be also star or delta. Now, the three phase voltage generation, three phases can be connected in delta also. As I say, in this case we have R 1 connected to Y, Y 1 connected to B and B 1 connected to R, and then at the junction point of Y to R 1 we have 1, and then we have Y 1 B to Y 1 one junction point and B 1 to R another junction point. So, we have this corresponding three terminals here, which gives us the corresponding three phase voltages. So, if you see here, the corresponding connection becomes a delta connected load, delta connected generations or source, which can be connected to the load through the conductors or cables. Now, if you see the corresponding waveforms in the omega t or theta in radian terms, then we have the corresponding up to 4 pi, this plot is there. So, we have red one, this is red, this is yellow, this is for the blue, and these are the corresponding voltages V r, V y and V b. You see how a star connected generation like R 1 R here, B 1 B here, Y 1 Y here. So, this is a star connected source, voltage source, and this is connected to the load through three wire system or three phase 3 wire system, and so the corresponding voltage developed by this takes like this R Y B, this red, yellow, blue, and the expression for this corresponding voltages can be E r equals to E m sin omega t, E y equals to E m sin omega t minus 120, E b equals to E m sin omega t minus 240. So, this we see here that all these three voltages are having a separation of 120 and 120 to each other. So, between R and Y we have 120 separation, between 1 and B we have 120 separation, and between B and R also we have 120 separation, like that. So, if we see this corresponding summation of all the three voltages, that becomes equals to 0, and see also that the corresponding magnitude of each one is having E m, E m and E m peak value. So, RMS value will be E m by root 2 and so. So, what we see here that such a supply system or voltage system is called a balance voltage system. So, what do you mean by balance here? That all are having the same magnitude or same peak value, and or RMS value also E m by root 2 happens to be there, and they are having 120 degree separation from each other between R and Y and between Y and B and between B and R, all are having 120 degree separation. So, such a system is called balance voltage system. Now, in the laboratory we will see the three phase waveform, the voltage waveform, the three phase supply system to our laboratory. For this, we see this in the oscilloscope, the corresponding supply system, and we see here
the R, Y, B, the corresponding voltage waveforms. So the corresponding phase sequence happens to be here also. After R, Y comes, then comes the blue. So the phase sequence is R, Y, B, that we see here. In addition to that, we see here the corresponding frequency here right now is 50.034 Hz, and the voltage of each phase voltage, not the line voltage. Phase voltage of red one happens to be 237.6 volt now right now, and the phase voltage of the Y one is 237.98 volt, and the blue one is having 233.38 volt. So there is some unbalance in the system also. That is very practical, and we see here the corresponding three-phase voltage supply system. So this is about the positive peak and this is about the negative peak. So from there also you can adjust about the voltage perspective and so. And as I already mentioned, the phase sequence happens to be red, yellow, blue.
Moving forward, in phasor terms, if we represent them the corresponding signals. So, these three signals E r equals to E m sin omega t r phase for r phase. The corresponding y phase lags the corresponding r phase by 120 degree. So, this becomes equals to E m sin omega t 120 degree, this is y phase voltage, and the third one, the B phase blue phase lags the corresponding y phase by another 120 degree. So, this becomes equals to your B phase E m sin omega t minus 240 degree. So, this is about the corresponding three waveforms we have seen in the earlier waveform diagram. So, each one, this is R, this is Y, this is B, and each one having 120 degree separation like that. So, therefore, between B and R we have 240 degree angle separation. Now, if we go to this phasor representation of this and I take the corresponding R phase as the reference, so that becomes equals to E m by root 2 0 degree. So, this will be E m by root 2 minus 120 degree, that is y phase, and B phase will be E m by root 2 minus 240 degree, or it can be represented in terms of E m by root 2 120 degree also. How? If this is V r phasor, if this is V y phasor, this is your minus 120 degree. So, this is lagging anticlockwise rotating phasor, these are phasors anticlockwise with a speed of omega. Now, what happens here for the V phase, B phase, then this will be lagging to the corresponding y phase by 120 degree. So, 120, 120, 240, this is minus 240 with respect to V r. So, from this side if we say this is plus 120. So, that is the same thing we are talking about. So, 120, 120, 120, total it becomes 360 degree. So, V r when you represent in terms of V r E m by root 2 0 degree, V y E m by root 2 minus 120 degree, V b becomes equals to E m by root 2 minus 240 degree or E m by root 2 120 degree. Now, this is about the phasor representation of the corresponding sinusoidal voltage quantity, three phase voltage quantities R, Y, B phases. Now, we call phase sequence. So, there are different terminology in three phase systems. Phase sequence R, Y, B. So, what do you mean by this? That the time order in which the phase voltages pass through their maximum value, here maximum value in the time order. So, R comes first, Y comes then, and then comes the B. So, the phase sequence becomes R, Y, B. Now, this is the time order in which this, or otherwise if we say phasors are anticlockwise rotating with a speed of omega. So, to this x axis the R phase crosses first, then comes the Y and then comes the B. So, R first, then Y, then B. So, that way also you can say that the corresponding phase sequence for this arrangement is R, Y, B. What we see here that the corresponding phase sequence here, the total sum of all the three voltages at any instant of time, total sum of all the three voltages E r plus E y plus E b in the time domain or the corresponding phasor domain, if we add all these three. So, that becomes equals to of this form and comes out to be 0. The phasor sum of voltage 0 and the instantaneous value of the corresponding at any instant of time if we see, then that becomes equals to 0. This is the property of the we call it balance voltage, and so we will elaborate more on this. So, the phase sequence as I said here, that becomes for this case is R Y B. Now, if I take another phasor domain, let us say this is A phase, phasors the corresponding 3 phase systems are being expressed in terms of A, B, C capital also, in terms of small a, b, c also. So, these are different terminology used for 3 phase system and so. So, if I say this becomes A phase, B A phase, and let us say this is V B phase and this is V C phase, then the phase sequence in this case becomes equals to A B C. So, this is anticlockwise rotating, A on the x axis, then comes B, then comes C. You can have another situation like let us say this is V R, this is V B phasor and this is let us say Y, V Y. Now, in this case R goes first, R, then comes B and then comes Y. So, the corresponding phase sequence becomes R B Y. So, that is the about the phase sequence in terms of that. Now, let us have a question on this. What is the phase sequence of the 3 phase voltages expressed by V R equals to 300 cos omega t plus 20 and V y equals to 300 cos omega t minus 220 and V b equals to 300 cos omega t minus 100 volt. So, if we see this, we can represent them in terms of phasors, that becomes easier for us. So, if I take V r equals to 300 by root 2 with an angle of 20 degree, then the other two phasors V y equals to 300 by root 2 with an angle of minus 220 degree and V b becomes equals to 300 by root 2 minus 100 degree. So, if I plot them, so this V r becomes equals to, if this is my x axis, real axis. So, this becomes my V r, this becomes my V b, V b minus 100. So, this is minus 100 and then this becomes equals to V y, V y equals to minus 220. But what I find that between each of them we find at 120 degree each other. So, the phasor position says that the x axis is being crossed by r first, then by the b and then by the y, agree. Otherwise, you can extend the idea also that after y who comes, after y again r comes, after y again r comes, then again b comes, then again y comes. So, this goes repeating. So, therefore, you can take any combinations here, it can be b, y, r, if first b crosses, then comes y, then comes r and like that. We can start with y, r, b also. So, this all these are you can say that the corresponding expression for this. So, we can say r b y, you can say b y r, you can say y r b, the corresponding phase sequence of the 3 phase system for this case. In general, we say by r, this is r b y in this case. Generally, our systems happens to be r y b in general we express, or a b c in general we express in terms of the phase sequence and so. So, for this case we say that based on the corresponding phasor rotation and the corresponding angle, we find the corresponding phase sequence to be r b y or b y r or y r b. A single phase system, a single phase load here is connected through line cables to a single phase source to 30 to 40, 120 volt, 60 hertz, 50 hertz and so. But a 3 phase system as shown here, having 3 single phase connections like what we will see here, having a 3 phase load, connected to this through the line cables and so. So, this is the load part, this is the source part to the line. So, single phase versus 3 phase. So, in this case we see that if this becomes your phase, this becomes your neutral, this is your r phase, this is your y phase, this is your b phase. Straightforward, if you see here, if you have 3 phase loads here, one load, second load, third load. For one load here for Z L, let us say we require two wires, phase and neutral, 2 wires, two connections, connecting wires or cables and so. But for three loads, such loads, we can we require 6 conductors. For single phase we require phase and neutral 2 wires. For 3 such loads we require 6 wires, whereas if you see here for the 3 loads we can connect them by only 3 wires. So, this is a straightforward advantage of 3 loads 3 phase load connection, and so in terms of the number of cables or number of wires. Now, we will discuss more on the 3 phase load connection. So, the load or the impedances can be connected in star or it can be connected in delta. So, these are the two options available to us. So, star connection or called the Y connection, or this is about the delta connection. So, what you did here to the star point, simply I can call it as small n or s. So, this impedance, another impedance, another impedance, and this is connected to the supply side, phase R, phase Y, phase B, 3 phase. Similarly, 3 phase supply R, Y, B and the impedances are connected in delta. So, we can connect them in delta, but note that same impedance when connected in same value of impedance or resistance connected in star and delta, they do not lead to the same power, which we have already seen in case of DC and AC also. So, we will analyze that also in more details. Now, we will have a concept of balance load. What do we mean by balance load and balance voltage? So, balance voltage we have seen earlier about we will see, and now we talk about the balance load now. Balance load having equal magnitude and phase separation by 120 degree. So, if you see here I r equals to I p 0 degree, I p having some value 10 with an angle of 0 degree, I y equals to I p 120 degree minus 120 degree and I b equals to I p with minus 240 degree. So, I can say like this, this is I r, 120 degree lagging is I y and this is 120 degree lagging is I b. So, phase sequence is R y b and all are having same magnitude of I p and 120 degree apart. So, this is called a balance load. This is called a balance load when the load currents are having same magnitude in the 3 phases, and if they are having 120 degree separation, then we talk about, we mention them as balance load. Load means current, load means current here. So, for example, here 50 with an angle of 0 degree ampere in R phase, Y phase 50 with angle minus 120 degree ampere and B phase 50 with an angle of minus 240 degree ampere. So, this is about the corresponding, all are having same magnitude 50 RMS value and all are having the 0 degree, 120 degree and 240 degree, 120 degree separation from each other. So, this is about the balance load. So, on the contrary, unbalanced load, when either the corresponding magnitude or the corresponding phase angle does not satisfy this above statement for balance load, then you call it as unbalanced load. Like 10 0 degree, 10 minus 100, this means that there is 120 degree is not happening, then 10 here is 10 minus 200. So, again here also 120 degree is not happening. So, even though the magnitudes are same, but 120 degree separation is not maintained. So, like the corresponding phasor diagram becomes like this. So, then we call them as unbalanced load. And I can say another example, 5 with an angle of 0 degree and 7.2 with an angle of minus 120 degree and 8 with an angle of plus 120 degree ampere, ampere, ampere. So, this is also unbalanced thing. Like I say that here the corresponding magnitudes are not same, even though the angles are maintained with 120 degree. Simply another example you can say that the corresponding 2.5 with an angle of 0 degree and then we have 2.5 with an angle of minus 120 degree ampere and then 2.4 with an angle of plus 120 degree or minus 240 degree ampere. Here only one phase current is also deviating from the magnitude of 2.5. So, this becomes an also unbalanced current or unbalanced load for the system. So, we have a star connected load. Let us will analyze for this. So, in this case the corresponding star connections. So, we have a source side with R, Y, B the corresponding phases, and the corresponding star loads are, let us say, the ZL load, and these 3 impedances are connected in the star manner. So, current will flow from the source to the this. So, the corresponding currents are I R, I Y and I B in the 3 phases. Now, however, we can connect, this is called 3 phase 3 wire system. We can have another one 3 phase 4 wire also, because this star point is available here to the generation side also, to the load side also. We can connect them with another wire called the neutral wire. So, this kind of 3 phase 4 wire systems we find in case of our distribution system, low voltage distribution system, we call LT system, low tension system, and so. So, these are the 2 options with star connection about the loads 3 phase 3 wire and 3 phase 4 wire. This is not possible in case of the delta connection, we will see. So, the 3 phase 4 wire system, as I said, red phase, yellow phase, blue phase and the neutral 4 wires are there. So, there are 4 wires here. This is a 3 phase motor, induction motor also. So, it is connected to the all the R, Y and B, the phase conductors, not to the neutral, straightforward. This is a single phase power socket, to the R phase and to the neutral it is connected. This is a LED bulb, it is connected to the Y phase and to the neutral, and then we have a blue phase connected to the phase, blue phase connected to the neutral. So, these are the 3 single phase load and this is a 3 phase load. The 3 phase load is directly connected to the 3 phases only, no requirement of neutral. So, this is about the 3 phase 4 wire supply system, how they are being connected and see. So, from this supply system, then if you are having a single phase house like 1 kilowatt, 2 kilowatt, then you are being provided with any of the phase R, Y or B and the neutral. So, phase or the neutral. So, this phase can be R or Y or B. So, that goes to the connection of the particular house and so. Now, we will see the KVL, how we can apply KVL to analyze the corresponding 3 phase load. So, let us say 3 phase load having a 3 phase 4 wire system, 3 phases, phase conductors and this is about the neutral wire. So, if you see this connection, let us say see the only R phase, similarly we can analyze for the other phases also. So, the corresponding IR current path becomes this, it becomes a closed path like this. So, if I say go by this, the IR that becomes equals to VR upon ZL0, VR, this is the voltage VR upon ZL0, V upon the Z. So, let us say I express the VR to be equals to Vp with an angle of 0 degree and Z the corresponding impedance happens to be phi degree. So, that becomes equals to Vp by Z with minus phi. So, therefore, the corresponding current through this path, the IR becomes equals to Ip with an angle of minus of phi degree. So, this IR becomes equals to Vpc, this becomes equals to minus of phi degree. Similarly, I can express the Iy, the Iy current, I can express in terms of this voltage is Vy. So, that is equals to Vp with a minus 120 degree, because I take the corresponding phase sequence to be RYB for this case. So, then the corresponding impedance offered by this path is in this path is nothing but ZL0. So, let us say ZL0 is expressed by Z phi. So, therefore, this corresponding current becomes equals to Ip with an angle of minus 120 plus phi. Similarly, for the Ib, the B part, the B phase, this also the corresponding path here is ZL0 and then the voltage is Vp minus 240 angle minus 240 upon Z with an angle of phi. So, the Ip becomes equals to minus 240 plus phi. So, the corresponding 3 currents are there. So, in the phasor plots we can say IR, Iy, this is 120 degree and this Ib, this is another 120 degree. So, that becomes equals to, we got the corresponding IR, Iy to be this. If we add all these things, that becomes equals to 0. So, that this corresponding IR, IY plus IB plus equals to 0, it means that the corresponding current here, if we apply KCL here, then the neutral current IN, that becomes equals to 0. So, then if the corresponding current becomes balance as pointed out here, then the current through the neutral in a 4 wire system becomes 0. So, this becomes redundant, we do not require the 4th wire. So, that is the one of the simple analysis by applying the Kirchhoff's voltage law through this each loop for the R phase and Y phase and B phase, we can find this corresponding relation. So, this is our starting point, slowly we will go for the different analysis into the system and so. So, like the corresponding voltage currents, balance current and so, what we say that we learn also that the corresponding voltage here. So, this is about the corresponding balance voltage. So, in the balance voltage we see here we express the corresponding voltage to be E m sin omega t, E m sin omega t minus 120 and E m sin omega t minus 240, and then all are having 120 degree separation, and the sum of this E b plus U I plus E b E r plus E b U I plus E b equals to 0. So, that implies that also the corresponding system is balanced. So, magnitude same, angle 120 degree. So, this is called the balance voltage supply system and so. So, that is the part of this like balance load and balance voltage. So, in overall in this lecture we learned about these corresponding things in terms of 3 phase systems, and the 3 phase system happens to be can be balance load, can be unbalanced load, can be having balance voltage, and similarly you can talk about the unbalanced voltage also having different either magnitude in terms of magnitude or in terms of the angle also. So, this is all about the exposed to 3 phase systems. In the next lecture we will go for the more detailed analysis. Thank you.